Welcome back, I'm that Chemist, and today we have 5 important papers in organic synthesis for the month of March 2023. The first paper for today is this paper where they add cyclobutadiene to alkenes. Some highlights of this paper include a new protocol to prepare cyclobutadiene, as previous methods for this were a little bit more harsh, but the authors developed a new protocol which is milder. Additionally, the synthesis of bicyclic systems from cyclobutadienes was reported via a 4+2 cycloaddition. This enabled the synthesis of derivatizable cyclobutanes, and the authors also reported the total synthesis of dipyperamide G. In terms of the different approaches that were possible, it had been reported that you could access it from this iron-tris carbonyl complex through an oxidative protocol. Unfortunately, when this is formed, it tends to dimerize in this endoselective fashion to what is essentially opened up cubane. Other chemistry can happen, leading to the formation of other complex products. However, it's possible to add this to an electron-deficient alkene and undergo a cycloaddition, which is what the authors are interested in. So what the authors wanted to do was try and access another protocol where they could access intermediate 6, oxidize it in some fashion, and then form their cyclobutadiene in situ. So the way that the authors did this was through designing their own protocol. Once they developed a route to make the cyclobutadiene, then they did some cycloadditions to make high-value products. So the synthesis of the reagent is pretty clever. Here we have a hetero-Diels-Alder reaction, which is driven through the elimination of CO2. Once we have this diaza compound, it's possible to do a 2+2 intramolecular cycloaddition to form compound 8A, which is their precursor that they use to generate cyclobutadiene in situ. Their paper demonstrates a lot of different examples. You can see these are all Michael acceptor derived, where they're electron-deficient alkenes, and there's even more examples in their paper if you want to see the full list of everything that they try. They also demonstrated some examples with heterocycles. Here's one example I showed here with this quinoline. Now, in terms of derivatization, this is where I think this method comes in handy the most. The most striking, of course, is this cycloaddition to perfluorobenzene, where they get this laterane type product, which I personally am intrigued by. Additionally, they could do other types of reactions, such as another Diels-Alder here through the elimination of SO2. They're able to add this dihydrotetrachlorobenzene motif. They are also able to hydrogenate this open to a cyclohexane. They can selectively reduce it with diimide generated in situ to generate this bis cyclobutane motif, and they also explore some other cool chemistry you can do with these, such as this ring opening metathesis. Now, I mentioned that the authors also reported a total synthesis. So the authors chose a recently reported natural product that was originally reported in 2015. They took one of their products from their chemistry, which is this bis piperinamide, and they were able to undergo oxidative cleavage to form the dialdehyde, and 2 Wittig reactions later, they're afforded with dipyperamide G. Dipyperamide G is a bioactive amide which shows promising cytotoxicity when used in conjunction with paclitaxel, also known as Taxol. I wonder if Reactis, today's sponsor, has any predictive ideas about how to synthesize dipyperamide G. First, we're going to build our molecule, dipyperamide G. After we searched for it, we can see that there's no structures found. When a structure isn't indexed in Reactis yet, we're still able to use the predict retrosynthesis tool. So if it isn't available in the literature, we can do an AI-based search that's going to give us some possible routes to make our molecules. You can even tell the AI which building block libraries to use in the predicted retrosynthesis it gives you. So we've submitted our job here. You can see that the prediction panel is currently in progress. And once it's done, it should give us multiple routes to the target compound. And here we go, it's done. There's 3 predicted routes. Why don't we look at those? So here are each of the 3 predicted routes, and if we don't like the way that it's being shown, we can actually click on Tree View and view it differently. It also has a score, which is the predicted likelihood that this route would work. So a score of 0.96 is a fairly high confidence that a sequence like this could work. This is just one way to view potential synthetic sequences to access the target molecule. Since this shows you multiple different synthetic approaches, you might find one that would work really well in your case, or it might just give you an approach you hadn't considered previously. I want to thank Reactis for their support of this channel. The second paper for today is the enantioselective addition of ethers to aryl halides. Some highlights of this work include the enantioselective functionalization of THFs, as well as photocatalysis featuring nickel-2, along with aryl and heteroaryl bromides, and this method featured excellent functional group compatibility. Some highlights of the scope are shown here. You can see there's a lot of different functional groups which are tolerated, such as esters, ketones, aldehydes, nitriles, and sulfones. And they also demonstrated that some heteroaromatic systems were also tolerated. Finally, they demonstrated some complex molecules, and they have even more examples in their paper if you want to see the whole thing. Now, in terms of neat stuff, one of the cool things that they figured out they could do is with different protecting groups on the alcohol of this hydroxytetrahydrofuran, they could get different regioselectivity using their reaction conditions. So when they had a benzoyl group on the hydroxy, they were able to get the blue hydrogen to react, forming product 51. However, if they had a TBS-protected alcohol, such as in the case of 52, they were able to selectively activate that blue hydrogen so that they get functionalization at that position. I personally find this quite appealing. If you find it appealing as well, make sure you let me know down in the comments. Now, in terms of the mechanism, I was quite impressed with this. I won't go into too much detail, but I will say that the authors isolated a complex derived from the oxidative addition of an aryl bromide to their nickel bound to their ligand. And when they tried reacting that with their substrate, or even a slightly oxidized version of their substrate, they didn't get any reactivity. Now, what they did do is they tried preparing another complex where instead the THF was activated by their photocatalyst. This added to their ligated nickel complex, and when they mixed this with an aryl bromide, this was able to form their product. So they've got a pretty clear mechanism here. They isolated these compounds as well, which I thought was pretty impressive. And in their full paper, they also do some DFT. So if you're interested in that, I'd encourage you to go check it out. The third paper for today is the synthesis of 1-aza-homocubane. The highlights of this include the 16-step synthesis of 1-aza-homocubane, which is 9 steps from a known protocol, with a 17% overall yield. Additionally, this is the synthesis of a new highly strained polycyclic hydrocarbon, and if you're a fan of cubane, you're definitely going to be a fan of this paper. It's been previously reported in the literature, 1,4-cubane dicarboxylic acid bismethyl ester is able to be converted to this aminocubane derivative. And through a series of steps, the authors were able to convert this into the aza-homocubane. I won't go into too much detail here because this is all fairly fundamental chemistry, but if you're interested in how they did this, I'd encourage you to check out the full paper. Now, in terms of the stability of their product, they found that if it was treated with an excess of HCl, it tended to ring open over time, even if it was stored in the fridge. However, if they stored the free amine in solution, it was found to be stable for over a month in the dark at room temperature. When they switched from the HCl salt to the triflate or the camphor sulfonate salts, they found that it was much more stable. Additionally, I wanted to mention here that they examined the pKa of this heterocycle compared to some other nitrogen-containing heterocycles. They also calculated the proton affinity. I just thought that I'd include this here in case this is of interest to any of the medicinal chemists watching. I know you're watching. I know there's some of you out there. The fourth paper for today is the route optimization of a new potential drug candidate from Pfizer. This is in OPRD, and if you haven't read OPRD, these are the people doing real chemistry, developing the reactions that we use for the compounds that matter to people. Some highlights of this paper include the optimization of the discovery route for PF070599013, and the first process route on an 11 kilogram scale of the final API is reported. So to give you a bit of context about this work, PF070599013 is a candidate which is somewhat similar to compound 1 shown here, tucaresol. The mechanism of this drug is through the stabilization of sickle cell hemoglobin when oxygen is bound to it. So one issue that can happen in sickle cell anemia is because of the shape of the hemoglobin, it can cause the sickled hemoglobin to polymerize, and this can be a major issue. So what these small molecule candidates are aimed at doing is stabilizing hemoglobin bound to sickled cells, sickled red blood cells, so that the polymerization is less likely to occur. I thought that this approach was really interesting, and I'd encourage you to check out the full paper if you want to read more details about that. But today we're here for the chemistry, so let's get into the chemistry a little bit. They had their initial discovery route, which utilized this quinoline N oxide, and through a Mitsunobu reaction, they install this heterobenzylic alcohol through inversion of the heterobenzylic center. Once this coupling was formed, they treat the N oxide with tosyl chloride, and then they do an amination reaction. Now, to get to their final compound 3, they need to make the 6-bromopyridine into a pyridinone, so they do that with sodium methoxide and methanol, and then they undergo cleavage with TMS iodide generated in situ to afford the pyridinone. But they wanted to get around using this high-energy intermediate 5, and they also didn't want to use TMS chloride on scale. So they had 3 different routes. Route A is the one we just discussed. They had another approach where maybe they'd install a tosylate on this heterobenzylic position, and then through displacement by this phenol, they would get their compound 7, which is just a few steps away. Or alternatively, it would be possible to undergo cross-coupling chemistry to form compound 7 from the corresponding bromoquinoline. They ran into some issues supplying the hydroxyquinoline on scale, and so they needed to prepare it. So to get from 15 to 16 and 17, they do a modified Fitzinger reaction. To get rid of these extra carboxylic acid groups, they just undergo a thermal decarboxylation. This coalesces compound 16 and 17 into compound 18. The next step was to do a benzylation at the oxygen. Unfortunately, they get a bit of an impurity where benzylation at the quinoline occurs, because of course it does. And in their earlier route, they had used an O acetate there, but they experienced some downstream issues when they did that. So they switched to the benzyl route for the multi-kilo synthesis of intermediate 12. In this route, they still have to go through the N oxide, and they couldn't source this other amine nucleophile that they were using originally. But fortunately, they found that this ammonium hexafluorophosphate worked fine for their purposes. So this was good. They deprotect with palladium on carbon and hydrogen, and that gives them compound 12. Additionally, when they were screening some of the other building blocks, they also were looking at the bis-Bok because the mono-Bok was kind of a pain to prepare. So their two ideal points here were compound 12, which is unbocked, and compound 23, which was bis-Bocked. I wanted to highlight some interesting commentary that this paper had. You can skip forward a little bit in the video if you don't want to hear this, but a lot of the time, if we were to encounter these problems in the lab, we would probably just move on, but they find a way to solve these problems. Having optimized reaction conditions, we turned our attention to the isolation of tosylate 13. A solubility screen identified isopropanol and methylterbutyl ether as antisolvents for tosylate 13. Now, this is a tosylate, remember? So we're going to learn a lesson about fundamental chemistry here. To our surprise, the material crystallized from IPA slowly, but steadily decomposed even under low temperature storage. Upon closer examination, we discovered that this instability stemmed from the reaction of tosylate 13, which is a powerful electrophile, with residual isopropanol, a nucleophile. This kind of seems obvious in retrospect, but most discoveries seem obvious in retrospect. This was an interesting thing to think about, and there's a couple other interesting anecdotes. For example, later in their synthesis, when they were trying to couple this tosylate with this hydroxyquinoline, they were originally using cesium carbonate, but they found that they could switch to potassium carbonate. Now, because they weren't doing lab scale chemistry anymore and they weren't doing magnetic stirring, when an overhead stirrer was used, they needed to control the size of the particles. Otherwise, the chemistry wasn't going to complete conversion. So they found that the particle size of 325 mesh potassium carbonate provided fast kinetics and complete conversion in 12 hours at 25 degrees Celsius, whereas granular potassium carbonate gave a much slower reaction rate and incomplete conversion even after 48 hours. So this is another interesting problem. I think this is something we don't often think about in bench scale synthesis. The particle size of your base can definitely play a role. I know I personally haven't screened particle size in any of the methods I've worked on, and I'd be interested to hear if any of you have in the comments. Another interesting thing they report here is that DMSO, it's also a good nucleophile, right? That sulfoxide oxygen, that's a good nucleophile. So maybe that tosylate will have issues with DMSO, which they want to use. So they found that when they premix it with DMSO, it caused issues. Normally, if I was in the research lab, that would mean, okay, this solvent's not an option. We got to find a different solvent instead. But these process chemists, they're smart. So what they do is, instead of charging it in DMSO, they just charge the rest of the reaction in DMSO, and then they add in as a solid in 5 portions, and this works totally fine. They even get their product in high purity, 98.7% EE. So, sometimes an incompatible solvent is just incompatible with one of your starting materials, and the order of addition matters. I'm going to say that one more time. The order of addition matters. If you haven't changed the order of addition before, it's probably something worth looking at if chemistry is causing some problems. The last anecdote from this that I wanted to include was this one here, where they're purifying ether 7, which is this one shown here. After the reaction was complete, an equal volume of water was added to the reaction mixture to precipitate ether 7 as a white solid. If water was introduced at ambient temperature or below, the product tended to gum and form small particles, leading to a slow filtration. In contrast, addition of water at 50 degrees Celsius eliminated the gumming issue and formed a slurry of large crystals that filtered easily. Unreacted starting materials were purged into the mother liquor to furnish ether product 7 in 94% yield with 99% purity. Again, unless I was following a protocol that specifically asked for a specific temperature quench, I would never try something like this, which is why I've included this anecdote in this video. If you find these things helpful, make sure you let me know down in the comments. This is the reaction that they're talking about. I have one more anecdote after this talking about how they removed the palladium. They wanted to avoid the palladium route because palladium contamination of the final API at high levels is a concern. All of this is to just say that they were able to get rid of it with some specialized washes after the reaction, and that removed the palladium down to low levels. So overall, this is the first generation of the process route. This is how they make their API. They make the tosylate on the heterobenzylic alcohol. They couple the quinoline with this tosylate using 325 mesh potassium carbonate, and then they're able to undergo hydrolysis of this bromopyridine using KOH with this palladium-mediated system. And then through the workup, they're able to get rid of palladium down to acceptable levels. And now they have 11 kilograms of this API, which has been advanced to clinical evaluation. So I really like this paper. If you want me to feature more OPRD on the channel in the future, make sure you let me know, because I find these really interesting and I still barely touched on this paper as a whole. Make sure you go and give it a read, especially if you found this kind of stuff interesting. OPRD is a journal which is really great, and definitely you want to give it a read sooner or later. The fifth and final paper for today is Organogel Organolithiums. In this paper, the authors stabilized organolithiums using hexatricontane as an organogel. This is just a linear straight chain alkane. It's just C36. This is just one long chain, and they were able to stabilize organolithiums extremely well. In fact, they were able to do room temperature storage of these organolithium organogels, and they could even dump it into water and still use it afterwards, which is really impressive. Here's a picture of what the gel looks like. This was another really important piece of work. It's well known that you can put wax on stuff to keep it from going off. One example of this is in fruit waxing. A lot of plants naturally do this as it is, but there's also artificial wax that can be added to make something like an apple, shown here, preserved even longer. This is something I didn't know about. I just kind of assumed that fruits had their own wax, but it turns out that they actually add wax to stuff, which is kind of obvious in retrospect. So this works for apples. Maybe it'll work for chemistry. Some ideas in this vein that have been explored before include the use of Buchwald type catalysts, which have been used in paraffin capsules. I think you can even get these from Aldrich now for a lot of different catalysts. And a couple authors had explored deputectic solvents to do similar sorts of reactions with organolithiums. The problem is, a lot of solvents like deputectic solvents or other organogels tend to have hydrogen bond donating groups, which wouldn't be compatible with organolithiums or Grignards. So what these authors wanted to do is use this straight chain alkane, which doesn't have any hydrophilic groups, and their thought was that that might be better suited for the work that they were doing. I'll briefly tell some of the story that Ben, one of the authors, told to me. Usually gels are made up of components that can interact via H bonding, but obviously that's not really compatible with organolithiums. So we tried C36H74, just a long chain alkane, and the gel formed, and we just looked at how far we could push the organolithium gel in terms of how long it could stay stable for. Peter dropped it in a bowl of water, and it still worked afterwards. What sort of reactions could we do with it? Expand that to incorporating ligands like T-meta or other organometallics like Grignards. So this was kind of the inspiration. So the reactivity of this in a nutshell is summarized here. So what they would do here is mix their organolithium, which in this case is phenolithium, with additional ditert-butyl ether and their hexatricontane up to a specific volume. In their supporting information, they talk about what mixtures are stable and what mixtures are unstable. So if you want to know why the ratios are what they are, I'd encourage you to take a look at their supporting information. Basically, what they had to do was find conditions for each organolithium where the gel was stable under ambient conditions with a given ratio of hexatricontane and ditert-butyl ether along with their organolithium. Once they make this, they heat it and cool it. They get this big block of gel. They even expose it to air and show how that impacts conversion. And in example 4 here, this is just a solution of phenolithium exposed to air without their gel. It completely decomposes after 1 day being exposed. However, when they have their organogel, this was able to last 18 hours and still have 95% conversion in a subsequent reaction with this acetophenone. But that's not all. You could even leave it for 25 days open to air and still get 92% conversion. So this is pretty clearly a massive benefit compared to existing storage for organolithiums. The consistency of these things are about a soft popsicle, according to Ben. And you could imagine that someone like Aldrich or another chemical supplier could formulate pellets of organolithiums that could be simply just weighed out, and then you have a known amount of your organolithium, which is way safer to handle. Especially given some of the accidents that have occurred when handling organolithiums before, this might be a way to make chemistry safer, especially on scale, which is something I'm sure all of us would like to see. In addition to phenolithium, they explored N-butyllithium. Following the same sort of protocol, you can see the types of conversions they get when the stuff was exposed to air for extended periods of time. Here's a picture of what one of the organogels look like. This is just a zoomed in picture of what you see in the manuscript, but I'd like to thank Ben for sending me this, as I thought you guys would appreciate to see what it looks like close up. He described the consistency of this as kind of like a soft popsicle. If you were to squish it in your hand, it would deform, but you can cut it with a razor blade and then it will work fine if you need to like cut chunks out for your chemistry. So the way that they do this is they premix their hexatricontane with their ditert-butyl ether. They add in their organolithium warm it till everything melts, then they cool it in an ice bath, and by doing this in a syringe, they're able to just like take the plunger out and plop out the whole organogel. They did this with both phenolithium and N-butyllithium. They explored some sec-butyllithium with limited success later in their paper, and the authors are currently examining tert-butyllithium for the same protocol. What they really wanted to get down to was a point where you could chop it up with a razor blade and use it for different reactions and show that it still worked. So that's what they did. They took their organogel phenolithium block, they chuck it into water, because what does phenolithium hate? Water. This was fine. They take it out, dry it off with a paper towel, cut it into 3 chunks, do 3 nucleophilic additions to this acetophenone, and these are their 3 conversions. Excellent conversion to the product. The fact that this tolerates water because of its organogel nature is really impressive, and I think it really highlights the utility of this. You would never in your right mind tell a researcher to throw some phenolithium into water and then use it for a reaction, but here we go. It works. I think this kind of highlights why you want to use this, and I don't think I even need to talk about any of this anymore, but I will. They also demonstrate that this still has your typical reactivity of N-butyllithium or phenolithium. Here you can see some prototypical reactions that you do with organolithiums. This works fine, and I look forward to their future work looking at tert-butyllithium. We only have a few honorable mentions for this month's important papers. If you enjoy the series, make sure you check out other videos on the channel, and maybe you should check out Reactis. It's a really cool tool that you definitely want to check out. Thanks for watching, and I hope you have a great day.